Hello there, and welcome. Tonight I want to take you somewhere special, somewhere quiet and profound, where the very fabric of reality whispers secrets that our everyday minds can barely grasp. It's late now, isn't it? Perhaps you're lying in bed, the weight of the day slowly lifting from your shoulders, your breathing beginning to slow and deepen. Outside your window, the world continues its ancient dance, the earth turning on its axis with a patient, steady rhythm that has carried us through countless nights just like this one. And here we are, you and I, about to explore one of the universe's most beautiful mysteries together. Before we drift deeper into tonight's journey, I'm curious about you. Where in the world are you listening from right now? Are you in a bustling city where the lights never quite fade? Or perhaps somewhere quieter, where you can see the stars through your window? What time is it there? Is it the deep of night? Or are you stealing a moment of rest in the afternoon? If you find yourself returning to these gentle explorations of physics and the cosmos, if these quiet wanderings help you drift into peaceful sleep, perhaps you'd like to follow along for more of these journeys. A gentle like or subscribe would mean we can continue exploring the universe's mysteries together, night after night, question after question. But there's no rush, no pressure. Just like the spin we're about to explore, some things in the universe simply are, without needing to push or pull. Tonight, we're going to talk about something that seems so simple at first: rotation, spinning, the gentle turning of things in space. Look around you, or better yet, close your eyes and imagine. Everything in our universe seems to love to spin. Planets pirouette around their axes, creating the rhythm of day and night that structures our lives. Moons waltz around planets in elegant orbital dances that have inspired poets and scientists alike for millennia. Galaxies themselves are vast, slowly turning Catherine wheels of stars, each one taking millions of years to complete a single stately rotation. Even here on Earth, in your everyday life, spinning is everywhere. The wheels of a bicycle, a coin flipped into the air catching the light as it tumbles, a child's toy top humming as it stands impossibly on its point, defying gravity through the magic of rotation. There's something deeply satisfying about watching things spin, isn't there? Perhaps it's because spinning objects have a kind of persistence, a determination to keep going. This is what physicists call angular momentum, a beautiful way of saying that once something starts spinning, it wants to keep spinning. It's like the universe's way of holding onto rotation, preserving it, cherishing it. A figure skater pulls in her arms and spins faster, but her total, angular momentum stays the same, conserved like a precious quantity that the universe refuses to let go of. This conservation of angular momentum is one of nature's most reliable rules, as dependable as the sunrise, as trustworthy as gravity itself. But now, let's begin to shrink our perspective, to zoom in from the cosmic scale of galaxies and planets to something much, much smaller. Imagine we're descending through scales of size like a gentle, controlled fall through dimensions of magnitude. We pass through the human scale, your hand, your fingernail. We shrink further, past the width of a human hair, past the size of cells with their busy molecular machinery. Smaller still, past bacteria, past viruses, down to molecules vibrating with thermal energy, and finally to atoms themselves, those fundamental building blocks that make up everything you see, everything you touch, everything you are. Here, in the realm of atoms, we find electrons. These tiny, almost impossibly small particles orbit the nucleus in ways that would seem familiar at first. After all, we often picture them like tiny planets circling a minute sun. But this is where our comfortable classical picture begins to blur and shift. Electrons don't really orbit in nice, neat circles or ellipses like planets do. Instead, they exist in probability clouds, regions of space where they might be found, spreading out like morning mist around the atomic nucleus. They're not solid little balls following predictable paths, but something far more mysterious, far more quantum. And yet, despite not being little spheres racing around in circles, electrons still somehow carry angular momentum from their orbital motion. We call this orbital angular momentum, and it comes in discrete, quantized amounts, specific values that the universe allows and nothing in between. It's as if the universe has decided that angular momentum at this scale can only come in certain denominations, like a cosmic currency that only comes in specific bills, with no way to make change. But orbital angular momentum is only part of the electron story, and this is where things become truly mysterious, truly wonderful. You see, electrons have another kind of angular momentum, something that doesn't come from their motion through space at all. We call it spin, and the name itself is already misleading, already a compromise between what we can imagine and what actually is. When physicists first discovered that electrons behave as if they're spinning, they naturally pictured them as tiny spheres, rotating around their own axes like microscopic planets. It seemed so reasonable, so intuitive. After all, a spinning charged sphere would create a magnetic field, and electrons do indeed behave like tiny magnets. The math seemed to work, at least at first glance. But then the problems began to emerge, quietly at first, like cracks in a beautiful but flawed theory. If electrons were really tiny spinning spheres, if we calculate how fast their surfaces would need to move to generate the observed magnetic effects, we get an impossible answer. The surface of the electron would need to move faster than the speed of light, and that's forbidden by Einstein's relativity, one of the most thoroughly tested theories in all of physics. The universe simply doesn't allow anything with mass to move that fast. It's not just unlikely or difficult, it's fundamentally impossible, written into the very structure of space-time itself. Moreover, if electrons were classical spinning spheres of charge, they should be constantly radiating electromagnetic energy as they spin. Any accelerating charge emits radiation. It's one of the basic rules of electromagnetism, but electrons in atoms don't radiate away their spin energy. They maintain their spin forever, unchanging, eternal, as permanent a property as their electric charge or their mass. This spin is not something electrons do, it's something electrons are. It's woven into their very identity, as fundamental as any property we can name. So here we are, faced with a beautiful paradox. Electrons have angular momentum that doesn't come from angular motion. They spin without spinning. They rotate without rotating. It's as if the universe is playing a gentle joke on our classical intuitions, showing us that at the quantum scale, things can have the essence of a property without having its form. The electron carries angular momentum as surely as a spinning top does, but without any of the actual spinning motion we associate with tops or planets, or anything else in our everyday experience. This intrinsic angular momentum, this spin, behaves mathematically exactly like angular momentum should. It adds and subtracts with orbital angular momentum according to the same rules. It's conserved in interactions, just like the angular momentum of spinning galaxies or orbiting planets. It precesses in magnetic fields like a tiny gyroscope, and yet it emerges from no motion that we can point to, no rotation we can visualize. It's as if the universe has decided that angular momentum is so important, so fundamental, that it builds it right into the basic particles themselves, independent of any motion through space. The discovery of spin revolutionized our understanding of matter. It explained the mysterious doubling of spectral lines that had puzzled spectroscopists, tiny splittings in the light emitted by atoms that suggested some additional structure, some hidden degree of freedom that nobody had anticipated. It explained why the periodic table has the structure it does, why elements behave chemically the way they do. It even explains the very stability of matter itself through something called the Pauli exclusion principle, which depends crucially on the fact that electrons have spin 1 too. But perhaps most mysteriously, most beautifully, spin reveals that particles like electrons live partly in a space we cannot see, cannot directly visualize, an internal space of quantum states that has its own geometry, its own rules of rotation and symmetry. This is the space of SU2, a mathematical structure that describes how spin states transform and rotate. And here's where things become even stranger. In this space, a complete 360-degree rotation doesn't bring you back to where you started. You need to rotate 720 degrees, twice around, to truly return home. Imagine that for a moment. Imagine an object that you have to turn around twice before it looks the same again. It's almost impossible to visualize with everyday objects, isn't it? And yet, this is exactly how spin 1-2 particles like electrons behave. They live in a world where geometry itself is different from what we experience, where the rules of rotation have an extra twist, an extra layer of subtlety that our macro-scale world doesn't prepare us for. This double rotation property isn't just mathematical abstraction, it has real, measurable consequences. In certain experiments with neutrons or electrons, you can actually observe the effects of this strange geometry. You can see interference patterns that depend on whether a particle has been rotated through 360 degrees or 720 degrees, even though to our classical eyes these should be the same thing. It's as if the particle keeps track of its rotations in a way that transcends our ordinary understanding of space. As we lie here tonight contemplating these ideas, it's worth pausing to appreciate the profound weirdness of what we're discussing. Every electron in your body, and there are roughly 10^28 of them, carries this mysterious spin. They're all participating in this strange dance, this rotation that isn't rotation, this angular momentum without angular motion. The hemoglobin in your blood works because iron atoms can exist in different spin states. The computer or phone you might have used today operates on principles that depend on the electron spin. Even the chemical bonds that hold your DNA together are influenced by the spin of electrons. We're surrounded by spin, immersed in it, made of it, and yet we can't see it, can't touch it, can't really even properly imagine it. It's one of those places where the universe gently but firmly tells us that our evolved intuitions, shaped by millions of years of dealing with medium-sized objects moving at medium speeds, simply aren't adequate for understanding reality at its deepest levels. And perhaps there's something beautiful in that limitation, something humble and wonderful about recognizing that the universe contains mysteries that stretch our minds beyond their comfortable boundaries. The mathematical framework that describes spin, quantum mechanics, is spectacularly successful. It predicts experimental results with stunning accuracy, often to 10 or 12 decimal places. Every test we've devised, every experiment we've performed, confirms that spin behaves exactly as the mathematics says it should. And yet, when we try to translate that mathematics back into everyday language, into images and metaphors we can grasp intuitively, we find ourselves speaking in paradoxes and contradictions. The electron spins but doesn't spin. It rotates but stays still. It has angular momentum but no angular motion. Some physicists and philosophers have suggested that this difficulty isn't a failure of our theories, but a glimpse into something profound about the nature of reality itself. Perhaps the universe isn't made of things that have properties in the way we usually think about it. Perhaps at the quantum level, properties like spin are more fundamental than the particles themselves. Maybe we should think of electrons not as tiny objects that possess spin, but as excitations in quantum fields that manifest as particles with spin. The spin isn't something added to the electron. It's part of what makes an electron in the first place. This shift in perspective, from particles as things with properties to particles as manifestations of properties, is part of the profound reconceptualization of reality that quantum mechanics demands. It's not just that the universe is stranger than we imagined. It's stranger than we can imagine, at least with our classical everyday concepts. And spin is perhaps the perfect example of this strangeness, this gentle insistence by the universe that we need new ways of thinking, new mathematical languages, new conceptual frameworks to understand what's really going on at the smallest scales. As we continue our journey tonight, we'll explore how physicists discovered spin, how they learned to measure it and manipulate it. We'll see how spin connects to magnetism, to the stability of matter, to the very structure of space and time. We'll venture into the abstract mathematical spaces where spin lives and rotates according to its own peculiar rules. We'll see how spin is used in modern technology, from MRI machines that peer inside our bodies to quantum computers that might revolutionize how we process information. But for now, in these opening moments of our exploration, let's just sit with the beautiful mystery of it all. Somewhere in the atoms that make up your pillow, your blanket, your own body, countless electrons are carrying their intrinsic angular momentum, their spin through the night. They're not spinning in any way we can visualize, and yet they behave exactly as if they were, following mathematical rules of perfect precision and reliability. They're participating in a kind of cosmic dance that we can describe with equations but can't quite picture, can't quite grasp with our hands or our everyday imagination. This is the universe we live in, not a clockwork mechanism of spinning spheres and predictable orbits, but something far more subtle, far more mysterious. It's a universe where properties can exist without their classical causes, where angular momentum doesn't require angular motion, where a complete rotation might not bring you back to where you started. It's a universe that speaks in mathematics more fluent than our words, that operates according to principles more subtle than our intuitions. And perhaps, as you lie there tonight, feeling the weight of your body against the bed, hearing your own breath slowly deepening, you can sense something of this mystery in your own being. You're made of spinning particles that don't spin, of quantum entities that defy classical description, of mathematical patterns made manifest in flesh and bone and thought. You are, in a very real sense, a collection of quantum mysteries, temporarily organized into a pattern complex enough to wonder about its own nature. The room around you seems solid, stable, unchanging. But at the quantum level, it's a ferment of activity, a dance of particles and fields, a shimmering tapestry of probability and potential. And through it all, like a persistent thread, runs the mystery of spin. This property that isn't quite what its name suggests. This angular momentum that emerges from no visible rotation. This fundamental feature of reality that we can measure but not quite imagine. So here we are, you and I, facing this gentle paradox together in the quiet of the night. We've established that electrons have something called spin, that this spin acts like angular momentum, but that electrons aren't actually spinning like tiny tops or planets. It's a contradiction that would seem impossible if we didn't have mountains of experimental evidence telling us it's true. Let's wade deeper into this mystery, slowly, carefully, like walking into a still lake at dawn, feeling each step take us further from the familiar shore of classical physics into the quantum depths where our usual rules begin to dissolve and reshape themselves. Our minds are pattern-seeking machines, evolved over millions of years to make sense of the world at human scales. When we hear that something has angular momentum, every fibre of our intuition insists that something must be rotating. It's not just a casual assumption, it's built into the very way we understand cause and effect. A spinning top has angular momentum because it's rotating. A planet has angular momentum because it's turning on its axis and orbiting the sun. A figure skater has angular momentum because she's spinning on the ice. In every case we can point to and say, look, there's the rotation, there's the motion that creates the angular momentum. This intuition is so strong that when physicists first encountered evidence that electrons have angular momentum beyond their orbital motion, they immediately assumed electrons must be spinning. It was 1925, and two Dutch physicists, George Uhlenbeck and Samuel Goudsmit, were trying to understand puzzling features in atomic spectra, the specific colours of light that atoms emit or absorb. These spectra showed a fine structure, a delicate splitting of what should have been single lines into closely spaced pairs. Something was causing each energy level to split slightly, as if there were some additional magnetic interaction happening inside the atom. Uhlenbeck and Goudsmit proposed a bold solution. What if electrons were not just point charges orbiting the nucleus, but tiny spinning spheres? If an electron were a small ball of charge rotating around its axis, it would create a magnetic field, just like a loop of electric current does. This magnetic field would interact with the magnetic field created by the electron's orbital motion, causing exactly the kind of energy splitting observed in the spectra. The math worked out beautifully. The electron would need to have exactly half a quantum unit of spin angular momentum, what we now call spin 1-2, to match the experimental observations. The idea was elegant and satisfying. It connected the microscopic world of atoms to the familiar physics of spinning objects. It explained not just the spectral lines, but also why electrons behave like tiny bar magnets, with a north and a south pole. For a brief moment, it seemed like the universe was more comprehensible than we'd feared, that even at the atomic scale, things worked according to principles we could visualize and understand. But then the problems began to emerge, and they were devastating to this classical picture. First, there was the issue of size. Experiments had already placed upper limits on how large an electron could be. If it had any size at all, it had to be incredibly tiny, far smaller than an atom. But if you calculate how fast the surface of such a tiny sphere would need to move to generate the observed angular momentum, you get a speed greater than the speed of light. Not just a little bit greater, but substantially so. And this isn't just practically impossible. According to Einstein's special relativity, it's fundamentally forbidden. Nothing with mass can travel at or faster than light speed. It's one of the absolute rules of our universe. You might think, well, perhaps the electron is even smaller than we thought, or perhaps the charge is distributed in some special way. But this leads to even worse problems. A spinning charged sphere, no matter how small, is constantly accelerating. Each point on its surface is continuously changing direction as it rotates, and accelerating charges radiate electromagnetic energy. This is one of the most fundamental results in classical electromagnetism. It's why radio antennas work, why synchrotrons produce intense beams of radiation, why any classical model of the atom with orbiting electrons would collapse in a fraction of a second as the electrons radiated away their energy and spiraled into the nucleus. But electrons don't radiate away their spin. An electron's spin is absolutely stable, as permanent and unchanging as its electric charge or its mass. You can have an electron sitting in perfect isolation for billions of years, and its spin will remain exactly the same. This isn't just a theoretical prediction. We can trap individual electrons in electromagnetic fields and monitor them for extended periods, and their spin never decreases, never radiates away, never shows any sign of being a classical rotation that should be losing energy. There's another problem too, perhaps even more fundamental. If electrons were really tiny spinning spheres, we should be able to orient their spin axes in any direction we choose, just like we can orient a spinning top or gyroscope. If I hand you a gyroscope, you can point its axis north, south, east, west, or any angle in between. The orientation is continuous. There are infinitely many possible directions, and you can smoothly rotate from one to another. But electron spin doesn't work this way at all. This became dramatically clear through one of the most important experiments in quantum mechanics, the Stern-Gerlach experiment, performed in 1922, even before Uhlenbeck and Goudsmit proposed their spinning electron model. Let me paint you a picture of this experiment, because it's both simple in concept and profound in its implications. Imagine a beam of silver atoms, emerging from a small furnace, travelling through a vacuum. Silver atoms were chosen because they have a single unpaired electron in their outermost shell, so the magnetic properties of the atom are essentially just the magnetic properties of that one electron. The beam passes through a region where there's a magnetic field, but not just any magnetic field, one that's deliberately made non-uniform, stronger at one end than the other. This non-uniform field exerts different forces on the north and south poles of each tiny atomic magnet, causing a deflection that depends on how the atom's magnetic moment is oriented. If electrons were classical spinning spheres, if their spin axes could point in any direction, you'd expect to see the beam spread out continuously. Atoms with spin pointing up would deflect one way, atoms with spin pointing down would deflect the opposite way, and atoms with spin at various angles would deflect by intermediate amounts, creating a smooth, continuous distribution on the detector screen. It would be like spraying water through a magnetic field. You'd get a continuous fan of trajectories. But that's not what happens. Not at all. Instead, the beam splits cleanly into exactly two spots. Just two. Every single atom goes either to the upper spot or the lower spot with nothing in between. It's as if the universe is telling us that spin, when measured along any particular direction, can only give one of two answers. Up or down, plus half or minus half, nothing else. There's no such thing as spin pointing at a 30-degree angle or a 45-degree angle when you actually measure it. The measurement always forces the spin to choose, up or down along whatever axis you've chosen to measure. This is deeply, fundamentally weird. Imagine if I told you that whenever you measured the direction a car was travelling, you could only ever get one of two answers, exactly north or exactly south, never northeast or west or any other direction. You'd think I was crazy, but that's exactly how spin behaves. It's quantized not just in magnitude, always exactly +2 for an electron, but also in its measurable orientation, always giving only discrete results when measured. What makes this even stranger is that you can choose any axis you want for your measurement. You can orient your Stern-Gerlach apparatus to measure spin along the vertical axis, and you get two spots, up and down. Rotate the apparatus to measure along a horizontal axis, and you still get exactly two spots, left and right, we might say. Tilt it at any arbitrary angle and still exactly two spots. The electron's spin seems to have this remarkable property of always giving a definite answer, up or down, along whatever axis you choose to measure. But the answer you get is probabilistic if the electron wasn't already aligned along that particular axis. This leads to one of the most counterintuitive aspects of quantum mechanics. Suppose you measure an electron's spin along the vertical axis and find it's up. Now you know with certainty that if you immediately measure again along the vertical axis, you'll get up again. The electron is in a definite spin-up along vertical state. But now suppose you measure along the horizontal axis. You'll get either left or right with 50-50 probability. Let's say you get left. Now the electron is in a definite spin left along horizontal state. But here's the kicker. If you now measure along the vertical axis again, you no longer know what you'll get. The horizontal measurement has somehow erased the information from the vertical measurement. You'll get up or down with 50-50 probability, even though you knew for certain it was up before the horizontal measurement. This is completely unlike anything in classical physics. If you measure which way a spinning top's axis points vertically, then measure it horizontally, the vertical component doesn't change. You can know both simultaneously. But with quantum spin, you can never know all three components, x, y, and z, simultaneously with perfect precision. The more precisely you know one component, the less you can know about the others. They are complementary properties, incompatible observables in the language of quantum mechanics. This complementarity is encoded in the mathematics through something called commutation relations. The spin operators for different directions don't commute. The order in which you apply them matters. Measuring spin x then spinny gives different results than measuring spinny then spin x. This non-commutativity is the mathematical expression of the physical fact that you can't simultaneously know all components of spin. It's not just that we're not clever enough to measure them all at once, it's that they don't all have definite values simultaneously. The uncertainty is built into the nature of spin itself. So what is spin really if it's not a tiny sphere rotating? The honest answer is that we don't have a classical picture that captures it correctly. Spin is a purely quantum mechanical property, something that emerges from the mathematics of quantum mechanics without any classical analogue. It's a degree of freedom that particles possess, a way they can carry angular momentum, but it doesn't correspond to any motion through ordinary three-dimensional space. The best we can say is that spin is an intrinsic form of angular momentum, as fundamental to particles as their mass or charge. Just as an electron has a definite mass, about 9.1 × 10^31 kilograms, and a definite charge, 1.6 10^19 coulombs, it has a definite spin, Gauss 2. This spin isn't something the electron does, it's something the electron is. It's woven into the very definition of what it means to be an electron. In the mathematical framework of quantum mechanics, spin emerges naturally from the requirement that physics should look the same, regardless of how we orient our coordinate system. This is a symmetry principle. The laws of physics shouldn't depend on whether we call a particular direction x or y or z, or on how we rotate our reference frame. When you combine this rotational symmetry with the principles of quantum mechanics, spin pops out as a necessary feature. Particles must transform in specific ways under rotations, and these transformation properties are what we call spin. But here's where things get even more interesting. The way spin 1-2 particles like electrons transform under rotations is genuinely bizarre. If you rotate an electron's quantum state by 360 degrees, a complete turn that would bring any classical object back to its starting configuration, the electron's quantum state picks up a minus sign. Its wave function becomes negative. To truly return the electron to its original state, you need to rotate it 720 degrees, 2 complete turns. This sounds like abstract mathematical nonsense, but it has real, measurable consequences. You can set up interference experiments where electron waves travelling along different paths interfere with each other. If one path involves an extra 360-degree rotation relative to the other, the interference pattern shifts in a way that reveals this sign change. It's not just theoretical, it's been observed many times in beautiful experiments with neutrons, electrons, and other spin 1-2 particles. To get some intuition for this strange behaviour, physicists often use an analogy called the plate trick, or belt trick. Take a plate or a book and hold it in your hand. Attach ribbons or belts from the plate to the walls around you. Now rotate the plate 360 degrees. You'll find the ribbons are twisted. But if you rotate the plate another 360 degrees in the same direction, for a total of 720 degrees, you can untwist all the ribbons without any additional rotation. The plate needs 2 complete turns to truly return to its original configuration relative to its surroundings. This analogy isn't perfect. Nothing in the classical world perfectly captures quantum behaviour, but it hints at the idea that there might be hidden connections, invisible ribbons connecting particles to the structure of space itself, that only become untwisted after a 720-degree rotation. In the mathematical language of quantum mechanics, these hidden connections are described by objects called spinors, which live in a space that's connected to our ordinary three-dimensional space but has this extra twist to it. The discovery that spin requires 720-degree rotations for a complete turn revealed something profound about the nature of space itself. Our usual three-dimensional space, where 360 degrees brings you back to where you started, is in some sense not the whole story. There's a covering space, a double cover, where you need to go around twice to truly return home. Electrons and other spin 1-2 particles are sensitive to this deeper structure of space in a way that classical objects are not. This brings us to a profound realization. Spin is teaching us that the universe has hidden dimensions, not in the science fiction sense of parallel worlds, but in the mathematical sense of internal spaces where quantum properties live and transform. The spin of an electron exists in an abstract two-dimensional complex vector space. When we measure spin along any axis, we're projecting this abstract quantum state onto our familiar three-dimensional world, and the result is always one of two values, up or down along that axis. Think about that for a moment. Every electron carries with it a little piece of abstract mathematical space, a two-dimensional complex vector space where its spin state lives. This isn't a space you can point to or travel through. It's an internal space, a space of possibilities, a space of quantum states. And yet, this abstract space has real, physical consequences. The way spin states rotate and transform in this space determines how electrons behave in magnetic fields, how they bond in molecules, how they conduct electricity in materials. We're beginning to see that spin, despite its name, isn't really about rotation in the ordinary sense at all. It's about symmetry, about the way particles transform under rotations, about hidden internal spaces that particles carry with them. When we say an electron has spin 1-2, we're not saying it's rotating at some particular speed. We're saying it transforms under rotations in a very specific way, a way that requires 720-degree rotations to return to the starting point, a way that only allows two possible measurement outcomes along any axis. This quantum mechanical understanding of spin has profound implications. It explains why electrons in atoms fill shells the way they do, leading to the periodic table of elements. It explains the magnetic properties of materials, from the ferromagnetism of iron to the exotic behavior of superconductors. It's essential for understanding how particles interact, how forces are transmitted, how the universe builds complexity from simple quantum rules. As you lie there in the darkness, perhaps you can feel a shift in your understanding. The solid world around you, the very atoms of your body, are not made of tiny spinning balls but of something far more abstract, far more mathematical. Every electron is a nexus where abstract mathematics meets physical reality, where internal quantum spaces manifest as measurable properties, where the strange rules of the quantum world build the familiar structures of our everyday experience. Let's return now to that pivotal experiment I mentioned, the Stern-Gerlach experiment, and walk through it more slowly, more carefully, feeling our way through the implications like someone exploring a dark room with outstretched hands, building a mental map of the quantum world one careful observation at a time. This experiment, performed first in 1922, before anyone even knew about spin, would become one of the most important tools for understanding this mysterious quantum property. It deserves our patient attention, our quiet contemplation, because within its simple setup lies a doorway to understanding how the universe really works at its smallest scales. Picture the original laboratory in Frankfurt, Germany, where Otto Stern and Walter Gerlach worked through the night, their breath visible in the cold air because they couldn't afford to heat the lab properly in those difficult post-war years. They had built an apparatus that seemed simple enough, a small furnace containing silver, heated until silver atoms boiled off into vapour. These atoms would stream out through a small opening, forming a beam that travelled through a vacuum chamber. The vacuum was important. They needed the silver atoms to fly straight and true, undisturbed by collisions with air molecules. The beam of silver atoms then passed through the most crucial component, a magnetic field created by specially shaped magnets. But this wasn't just any magnetic field. Stern and Gerlach had carefully designed their magnets to create a field that was stronger at one pole than the other, what physicists call a non-uniform or inhomogeneous field. This non-uniformity was the key to the whole experiment. A uniform field would affect all the atoms equally, but a non-uniform field would exert different forces on atoms depending on their magnetic orientation. Think of it this way. Imagine you're holding a bar magnet near another bar magnet. If the field is the same everywhere, the pull on the north pole of your magnet exactly balances the push on the south pole, and the magnet doesn't experience any net force. It might rotate to align with the field, but it won't be pulled in any particular direction. But if the field is stronger at one end, then one pole of your magnet feels a stronger force than the other, and the whole magnet gets pulled toward or pushed away from the strong field region. This is exactly what Stern and Gerlach were counting on. Silver atoms were chosen carefully. A silver atom has 47 electrons, and the way these electrons arrange themselves in shells around the nucleus means that 46 of them pair up, their magnetic moments cancelling each other out. But there's one electron left over, unpaired, in the outermost shell. So magnetically speaking, a silver atom behaves essentially like a single electron. Whatever magnetic properties that lone electron has, that's what the silver atom displays. It was an elegant choice, a way to study single electron behavior using whole atoms that were easier to work with than bare electrons. According to classical physics, if atoms were tiny magnets with randomly oriented magnetic moments, the beam should have spread out into a continuous smear when it hit the detector. Some atoms would have their magnetic moments pointing up and would be deflected upward. Some would point down and be deflected downward. Most would point at various angles and be deflected by intermediate amounts. The result should be a continuous distribution, perhaps bell-shaped, spreading from maximum upward deflection to maximum downward deflection. But when Stern and Gerlach developed their detector plate, they saw something that made them question their equipment, their technique, perhaps even their sanity. The beam had split into exactly two distinct spots. Not a continuous smear, not a bell curve, but two sharp, distinct regions where the silver atoms had struck the detector. Half the atoms had gone to one spot, half to the other, with nothing, absolutely nothing in between. At first, they thought something must be wrong. They checked their vacuum, thinking perhaps air currents were affecting the beam. They adjusted their magnets, wondering if the field wasn't uniform enough. They tried different temperatures, different beam intensities, different everything. But always the same result. Two spots, just two, as if the universe was insisting on this discrete binary outcome. It was, as Stern would later say, the most impressive experiment of his life, though at the time he had no idea what it meant. What it meant, we now understand, is that the magnetic moment of the electron, and therefore its angular momentum, is quantized not just in magnitude but in its measurable direction. When you measure the component of spin along any axis, you always get one of exactly two values, +2 or p2, which we often call spin up and spin down for convenience. There are no intermediate values, no 3/4 up or 1/3 down. The universe, at least at the quantum level, is digital rather than analog when it comes to spin measurements. But here's where things get even more interesting. You can rotate your Stern-Gerlach apparatus to measure spin along any axis you choose, vertical, horizontal, or any angle in between. And no matter what axis you choose, you always get exactly two spots. If you measure along the vertical axis, you get spin up and spin down along vertical. If you then take those atoms you measured as spin up along vertical and pass them through a horizontal Stern-Gerlach apparatus, they split again into two groups. Half go to spin left along horizontal, half to spin right along horizontal. This leads to a profound insight. The electron's spin state can't be described by simply saying, the spin points in this direction. Instead, the spin exists in a superposition of possibilities until measured. When you measure along a particular axis, you're not revealing a pre-existing direction. You're causing the spin to choose one of the two allowed values along that axis. The act of measurement doesn't just observe the spin, it fundamentally changes it, collapsing the superposition into a definite state. We can make this even more dramatic with a series of Stern-Gerlach devices. Imagine we set up 3 devices in a row. The first measures spin along the vertical z-axis. We block the spin-down beam and only let the spin-up atoms through. Now all our atoms are definitely spin-up along z. The second device measures spin along the horizontal x-axis. The beam splits into 2. Half the atoms go spin left, half go spin right along x. Let's block the right beam and only let the left beam through. Now all our atoms are definitely spin left along x. Here comes the surprise. The third device measures spin along the vertical z-axis again. Classical intuition says that since we selected only spin-up atoms in the first device, they should all still be spin-up. But that's not what happens. The beam splits again. Half the atoms are now spin-up along z, and half are spin-down along z. The measurement along x has somehow erased the information about the z component of spin. The atoms no longer remember that they were originally selected to be spin-up along z. This is completely unlike anything in our everyday experience. If you sort a deck of cards into red and black, then sort the red cards into hearts and diamonds, the hearts are still red. The second sorting doesn't undo the first. But with quantum spin, measuring along one axis genuinely disturbs and randomizes the spin along other axes. It's not that we're clumsily disturbing the system with our measurement. This disturbance is a fundamental feature of quantum mechanics, encoded in the mathematics through the non-commuting nature of spin operators for different directions. Let me describe another beautiful experiment that reveals the strange nature of spin, electron spin resonance, or ESR. In this technique, electrons are placed in a strong magnetic field. The spin-up and spin-down states now have slightly different energies. The spin-up state, aligned with the field, has lower energy, while the spin-down state, anti-aligned with the field, has higher energy. The energy difference is tiny but precisely determined by the strength of the magnetic field and the magnetic moment of the electron. Now we shine electromagnetic radiation, typically microwaves, on these electrons. When the frequency of the radiation exactly matches the energy difference between spin-up and spin-down states, something remarkable happens. The electrons absorb the microwave photons and flip their spins. A spin-up electron absorbs a photon and becomes spin-down. It's like a perfectly tuned resonance, hence the name electron spin resonance. What's beautiful about ESR is how precisely it works. The resonance frequency is exactly what quantum mechanics predicts, down to extraordinary precision, parts per billion or better, and the electrons don't absorb radiation at any other frequency. It's not like they absorb a little bit at nearby frequencies. The absorption is sharply peaked at exactly the resonance frequency. This precise quantization of energy absorption is another fingerprint of the quantum nature of spin. ESR has become an invaluable tool in chemistry, biology, and materials science. It can detect unpaired electrons in molecules, revealing details about chemical reactions, the structure of proteins, the defects in crystals. Every ESR spectrum is a direct probe of electron spin, a window into the quantum mechanical heart of matter. And every successful ESR experiment is another confirmation that spin, whatever it is, behaves exactly as quantum mechanics predicts. Even more remarkably, the same principle works for nuclear spins. Many atomic nuclei also have spin. The proton, for instance, is another spin 1-2 particle. Nuclear magnetic resonance, or NMR, uses the same basic idea as ESR but applied to nuclear spins. And NMR in turn is the basis for magnetic resonance imaging, MRI, the medical scanning technique that can peer inside your body without harmful radiation. Think about that for a moment. The same quantum mechanical property that seemed so abstract, so removed from everyday experience, this strange intrinsic angular momentum that isn't really angular motion, is what allows doctors to diagnose injuries, detect tumours, map the functioning of your brain. Every MRI scan is a practical application of spin, a technology that depends on the fact that protons in hydrogen atoms, and your body is full of hydrogen, especially in water and fat, are little quantum magnets that can be flipped by precisely tuned radio waves. The development of MRI is a beautiful example of how the most abstract, seemingly impractical discoveries in physics can lead to transformative technologies. When Stern and Gerlach were shivering in their cold lab, watching silver atoms split into two beams, they couldn't have imagined that their discovery would one day help save lives. When physicists in the 1940s were working out the theory of nuclear magnetic resonance, they weren't thinking about medical applications. They were just trying to understand the quantum mechanical behavior of nuclear spins. But let's return to the fundamental experiments that revealed the nature of spin. Another crucial set of observations came from atomic spectroscopy, the study of the light emitted or absorbed by atoms. When you heat an element or run electricity through it, it emits light at very specific wavelengths, creating a spectrum as unique as a fingerprint. These spectra were a major puzzle in the early 20th century. Why did atoms emit only certain colors? Why were the patterns so precise and reproducible? The development of quantum mechanics explained the basic structure of these spectra. Electrons in atoms can only occupy certain energy levels, and when they jump between levels, they emit or absorb photons with exactly the energy difference between the levels. But when spectroscopists looked more carefully, with better and better instruments, they found that many spectral lines were actually split into multiple, closely spaced lines. This fine structure, as it came to be called, was another mystery. The key to understanding fine structure was recognizing that electrons have spin. The spin creates a magnetic moment, and this magnetic moment interacts with the magnetic field created by the electron's orbital motion around the nucleus. It's as if the electron is a tiny bar magnet moving through the magnetic field of its own orbital motion. This spin-orbit coupling, as it's called, slightly shifts the energy levels, creating the fine structure in the spectra. The amount of splitting depends on the relative orientation of the spin and orbital angular momentum. They can be aligned or anti-aligned or at various angles, and each configuration has a slightly different energy. The mathematics of how spin and orbital angular momentum combine, adding as vectors but with quantum mechanical rules, perfectly predicts the observed fine structure patterns. Every spectral line split, every tiny shift in wavelength, is a testament to the reality of electron spin. But perhaps the most profound experimental confirmation of spin's strange properties comes from tests of the Pauli exclusion principle. Wolfgang Pauli proposed in 1925 that no two electrons in an atom can have exactly the same quantum state. Since electrons are spin 1-2 particles, each orbital can hold at most 2 electrons, one with spin up and one with spin down. This simple rule explains the entire structure of the periodic table, the patterns of chemical bonding, the very existence of chemistry as we know it. The exclusion principle isn't just a rule about electrons in atoms, it applies to all particles with half-integer spin, what we call fermions. Protons, neutrons, neutrinos, quarks all obey the exclusion principle, and this principle is intimately connected to the strange 720-degree rotation property of spin 1-2. There's a deep theorem in quantum field theory, the spin statistics theorem, that proves that particles requiring 720-degree rotations to return to their original state must obey the exclusion principle, while particles that return to their original state after 360-degree rotations, integer spin particles or bosons, do not. The experimental evidence for the exclusion principle is everywhere. The stability of matter itself depends on it. Without the exclusion principle, all the electrons in an atom would collapse into the lowest energy orbital. Atoms would be much smaller, matter would be much denser, and chemistry as we know it wouldn't exist. The fact that you exist, that your body is made of stable atoms arranged in complex molecules, is a direct consequence of electron spin and the exclusion principle. We can see the effects of spin in the magnetic properties of materials too. Some materials, like iron, are ferromagnetic. They can be permanently magnetized. This happens because the spins of unpaired electrons in iron atoms prefer to align parallel to each other. When enough of these spins align in the same direction, their tiny magnetic moments add up to create a macroscopic magnetic field. Every permanent magnet is a manifestation of electron spin, billions upon billions of tiny quantum magnets all pointing the same way. Other materials show different magnetic behaviors. In paramagnetic materials, spins align with an external magnetic field, but don't interact strongly with each other. In antiferromagnetic materials, neighbouring spins prefer to point in opposite directions. In ferromagnetic materials, you have 2 types of atoms with different magnetic moments, leading to complex magnetic structures. Each of these behaviours emerges from the quantum mechanical properties of spin and how spins interact with each other and with external fields. One of the most striking demonstrations of spin comes from experiments with spin-polarized beams. Using various techniques, physicists can create beams of particles where all the spins point in the same direction. When these polarized beams scatter off targets, the scattering patterns depend on the spin orientation in ways that classical physics could never predict. These spin-dependent scattering experiments have revealed details about nuclear forces, the structure of nucleons, and the fundamental interactions between particles. In the 1970s and 1980s, physicists developed techniques to measure the spin of individual electrons. Using devices called quantum dots, tiny islands of semiconducting material that can trap single electrons, researchers could observe individual spin flips, watch single spins precess in magnetic fields, even use individual spins as quantum bits for quantum computing. These experiments take us as close as we can get to seeing spin directly, though of course what we're really seeing are the effects of spin, not the thing itself. More recently, experiments with ultra-cold atoms have allowed physicists to create and study exotic states of matter where spin plays the central role. Bose-Einstein condensates of atoms with integer spin, degenerate Fermi gases of atoms with half-integer spin, synthetic magnetic fields that affect neutral atoms as if they were charged. All of these depend crucially on the quantum mechanical properties of spin. These experiments are not just confirming what we already knew about spin. They're revealing new phenomena, new states of matter, new ways that spin can manifest in the quantum world. Every one of these experiments, from the original Stern-Gerlach to the latest ultra-cold atom studies, tells the same story. Spin is real, it's quantized, it behaves exactly as quantum mechanics predicts, and it's definitely not classical rotation. The experimental evidence is overwhelming, precise, and consistent across scales from individual electrons to macroscopic magnets, across temperatures from near absolute zero to thousands of degrees, across systems from simple hydrogen atoms to complex biological molecules. As you lie there in the quiet darkness, perhaps you can appreciate the weight of all this evidence. It's not just one or two experiments suggesting that spin is this strange, non-classical property. It's thousands of experiments, millions of observations, all pointing to the same conclusion. The universe really does have this hidden angular momentum, this intrinsic spin that emerges not from motion, but from the fundamental nature of particles themselves. And perhaps there's something comforting in this consistency, this reliability. The quantum world may be strange, it may defy our classical intuitions, but it's not arbitrary or chaotic. It follows precise rules, mathematical laws that we can discover and verify and use. Every MRI scan that helps diagnose a disease, every computer hard drive that uses giant magnetoresistance to read data, every chemistry reaction that depends on electron spin, they all work because spin behaves exactly as quantum mechanics says it should, strange as that behavior might be. Now we come to something even deeper, even more mysterious. We've seen that spin behaves like angular momentum, but isn't caused by actual rotation. We've seen the experimental evidence that spin is real and quantized. But to truly understand spin, we need to venture into the abstract mathematical spaces where it lives, the hidden geometry that governs its behavior. Don't worry, we'll travel slowly, carefully, using images and analogies to light our way through these abstract realms. Think of it as exploring a vast, darkened cathedral with a candle, revealing the architecture one small pool of light at a time. Let's begin with something familiar, ordinary angular momentum, the kind that comes from things actually rotating or orbiting. When the Earth spins on its axis, it has angular momentum. When it orbits the Sun, that's another form of angular momentum, orbital angular momentum. In classical physics, angular momentum is a vector, which means it has both a magnitude, how much angular momentum, and a direction, the axis around which the rotation happens. You can picture it as an arrow pointing along the axis of rotation, with the length of the arrow representing how fast the spinning is happening. In quantum mechanics, orbital angular momentum works similarly, but with crucial quantum modifications. An electron orbiting an atomic nucleus has orbital angular momentum, but it can't have just any value. The magnitude is quantized, restricted to values like 0, 2, 6, 12, and so on, specific values determined by the quantum number L. The component along any chosen axis is also quantized, restricted to integer multiples of 0 plus 2 up to plus L. These are the rules for orbital angular momentum, and they emerge naturally from solving the Schrödinger equation for an electron in an atom. But here's the remarkable thing. Spin follows almost exactly the same mathematical rules as orbital angular momentum, even though it doesn't come from any orbital motion. The mathematics is nearly identical. Spin has a magnitude, and for an electron this magnitude is always 314. That's SS+1, where S tend 1 or 2. When you measure the component of spin along any axis, you get plane 2, the way different components of spin relate to each other, the way spin behaves in magnetic fields, the way multiple spins combine. It all follows the same mathematical framework as orbital angular momentum. This mathematical similarity is telling us something profound. It's saying that spin and orbital angular momentum are different manifestations of the same underlying thing, angular momentum in quantum mechanics. They're like different instruments playing the same musical theme, different expressions of the same fundamental symmetry of nature. The universe seems to be telling us that angular momentum is so fundamental, so important, that it builds it into particles in multiple ways, through their motion and through their intrinsic properties. But to really understand spin, we need to talk about symmetry. Symmetry is one of the most powerful concepts in physics. A sphere has rotational symmetry. It looks the same no matter how you rotate it. The laws of physics have rotational symmetry too. They work the same way whether you're facing north or south, whether your laboratory is oriented this way or that. This rotational symmetry of physical laws is intimately connected to the conservation of angular momentum. It's a deep principle, proven by a brilliant mathematician named Emmy Noether, that every symmetry in physics corresponds to a conserved quantity. Rotational symmetry gives us conservation of angular momentum. Now, when we rotate things in three-dimensional space, we're performing what mathematicians call a rotation operation. The set of all possible rotations in 3D space forms what's called a group, specifically the group SO3, which stands for Special Orthogonal Group in 3 dimensions. Don't let the terminology intimidate you. Think of it as the collection of all possible ways to rotate an object, with rules for how rotations combine. If you rotate something 30 degrees around one axis, then 45 degrees around another axis, that's equivalent to some single rotation around some third axis. The group SO3 captures all these relationships. But here's where things get strange and beautiful. When we look at how quantum mechanical spin states transform under rotations, we find they don't quite follow SO3. Instead, they follow the rules of a related but different group called SU2, Special Unitary Group in 2 dimensions. SU2 is like SO3's mysterious twin, similar but with a crucial difference. In SO3, rotating 360 degrees brings you back to where you started. In SU2, you need to rotate 720 degrees to truly return to the beginning. Imagine, if you can, a space where directions are more subtle than in our ordinary world. In our 3D space, if you point in some direction and then rotate 360 degrees, you're pointing in the same direction again. But in the space where spin lives, after a 360-degree rotation, you're pointing in what seems like the same direction, but there's a hidden difference. The quantum state has picked up a minus sign. Only after 720 degrees do you truly return to the identical quantum state you started with. This isn't just abstract mathematics. This minus sign has real, measurable consequences. In certain interference experiments, you can split a beam of neutrons, rotate one beam by 360 degrees relative to the other, and then recombine them. The beams interfere destructively where they would have interfered constructively without the rotation, and vice versa. The 360-degree rotation has introduced a relative minus sign between the beams, changing the entire interference pattern. It's a direct observation of SU2 symmetry in action. To get some intuition for this strange behavior, physicists often use the analogy of a Mobius strip. Take a strip of paper, give it a half twist, and tape the ends together. Now imagine an ant walking along the strip. After going once around, the ant is back at the same point but on the opposite side of the strip. Though of course a Mobius strip only has one side, that's what makes it special. The ant needs to go around twice to truly return to its starting configuration. Spin 1-2 particles are like that ant, except they're travelling through an abstract space of quantum states rather than along a paper strip. Another helpful analogy involves your own arm. Hold your arm out with your palm facing up. Now rotate your hand 360 degrees by twisting your arm. Your hand is back in the same orientation, but your arm is twisted. Rotate another 360 degrees in the same direction, and remarkably, you can untwist your arm, you might need to loop it around, without any additional rotation of your hand. Your hand needed 2 complete rotations to return both itself and your arm to the starting configuration. This is sometimes called the plate trick, or belt trick, and While it's not a perfect analogy for spin, it captures something of the two-rotation mystery. The mathematical objects that transform according to SU2 are called spinors. Where vectors in ordinary space have three components, x, y's, spinors have two complex components. You can think of a spinor as a more subtle kind of arrow, one that knows not just what direction it points, but also how many times it has been rotated. Spinors are the natural language for describing spin-1,2 particles. The quantum state of an electron spin is a spinor, and all the strange properties of spin, the two-valuedness of measurements, the 720-degree rotation needed for a complete turn, emerge naturally from the mathematics of spinors. What's remarkable is that ZU2 is actually more fundamental than SO3. There's a mathematical relationship where ZU2 covers CO3 twice. Every rotation in 3D space corresponds to two different elements of SU2, differing by a minus sign. It's as if our familiar 3D rotations are just shadows of something more complete, and spin-1,2 particles can see the full structure while classical objects only see the shadow. This relationship between SU2 and SO3 has profound implications. It tells us that the universe has a hidden doubling in its rotational structure, a subtlety that only quantum particles can detect. Classical objects and particles with integer spin only see the SO3 structure. They return to themselves after 360 degrees, but particles with half-integer spin see the full SU2 structure and need 720 degrees to complete their journey. The fact that nature uses SU2 rather than just SO3 is one of those deep mysteries that physicists have learned to accept and work with, even if we don't fully understand why. Why should the universe have this hidden complexity in its rotational symmetry? Why should some particles, fermions, see the full SU2 structure while others, bosons, only see SO3? These questions touch on some of the deepest issues in physics, connecting to the nature of space, time, and matter itself. When we combine multiple spins, the mathematics of SU2 tells us exactly how to do it. Two spin-1,2 particles can combine to give either total spin 0, a singlet state, where the spins are opposite, or total spin 1, a triplet state, where the spins are aligned. The rules for combining spins, called Klebisch-Gordon coefficients in the physics literature, are completely determined by the structure of SU2. Every possible way that spins can combine, every allowed total spin state, emerges from the mathematics of this symmetry group. This combining of spins is crucial for understanding atoms, molecules, and materials. In a helium atom, the two electrons can be in a singlet state, opposite spins, total spin 0, or a triplet state, aligned spins, total spin 1. These different spin states have different energies and different chemical properties. The stability of the helium atom, the reason it's chemically inert, is intimately connected to how the two electron spins combine according to SU2 rules. In molecules, electron spins from different atoms can couple together, creating complex patterns of spin states. The way these spins interact, mediated by the electromagnetic forces between electrons, determines molecular structure, chemical reactivity, and spectroscopic properties. Every chemical bond involves a delicate dance of electron spins, choreographed by the rules of SU2 symmetry. The connection between spin and rotations goes even deeper when we consider special relativity. In relativistic quantum mechanics, space and time are united into spacetime, and rotations are part of a larger symmetry group called the Lorentz group, which includes both rotations and boosts, changes of velocity. The representations of the Lorentz group, the ways particles can transform under rotations and boosts, are classified by two numbers, mass and spin. Every elementary particle is characterized by these two numbers. An electron is the spin 1,2, mass 5 to 11 keV-C2 representation of the Lorentz group. A photon is the spin 1, massless representation. This classification of particles by their transformation properties under spacetime symmetries is one of the most beautiful insights in physics. It tells us that spin isn't just some arbitrary property that particles happen to have. It's a fundamental aspect of how particles exist in spacetime, how they transform under the symmetries of special relativity. In a very real sense, spin is telling us about the shape of spacetime itself, about the hidden geometry that underlies our universe. The mathematics of SU2 also appears in many other areas of physics, often in surprising ways. In nuclear physics, the proton and neutron can be thought of as two states of a single particle, the nucleon living in an abstract isospin space that has the same SU2 structure as ordinary spin. In particle physics, the weak nuclear force is described by an SU2 gauge symmetry. Even in condensed matter physics, SU2 symmetries appear in the description of superconductors, quantum Hall systems, and topological insulators. It's as if the universe has a deep love affair with SU2, using this mathematical structure over and over again in different contexts. Each time it appears, we get phenomena that involve two-state systems, doublets, and that characteristic 720-degree rotation property. The universality of SU2 suggests it's not just a mathematical tool we use to describe nature, but something fundamental about the way nature organizes itself. As we lie here contemplating these abstract spaces and hidden symmetries, it's worth pausing to marvel at the human mind's ability to uncover them. We evolved to deal with medium-sized objects moving at moderate speeds, to track prey and avoid predators, to navigate through three-dimensional landscapes. Nothing in our evolutionary history prepared us to think about spinors or SU2 symmetry. And yet, through careful experiments and mathematical reasoning, we've discovered these hidden structures that govern the universe at its smaller scales. The journey from Stern and Gerlach's split beam of silver atoms to our modern understanding of SU2 symmetry is a testament to human curiosity and ingenuity. Each step required letting go of classical prejudices, accepting experimental results that seemed impossible, and following the mathematics wherever it led. The result is a picture of reality far stranger and more beautiful than anything our ancestors could have imagined. We return once more to the central mystery, but now with deeper understanding, like revisiting a familiar path after years of travel and seeing details we missed before. Spin is not literally spinning, yet it behaves like angular momentum. It lives in the abstract space of SU2, requiring 2 full rotations to return to its starting point. Let's dwell in this strange landscape a while longer, feeling our way through its peculiar geometry, learning to be comfortable with its paradoxes. Imagine you're holding a compass, but not an ordinary compass. This is a quantum compass, one that can detect the orientation of an electron's spin. When you measure with this compass along any direction, you get one of only 2 readings, up or down along that axis. But here's the strange part. Between measurements, the spin isn't pointing in any definite direction at all. It exists in what physicists call a superposition, a quantum state that contains the potential for all possible measurement outcomes without being committed to any single one. This superposition isn't just ignorance about which way the spin really points. Experiments have proven definitively that the spin genuinely doesn't have a definite direction until measured. It's not like a coin that's either heads or tails even when we're not looking. It's more like a coin that's somehow both heads and tails, neither heads nor tails, until the moment we observe it. And the act of observation doesn't reveal a pre-existing value, it causes the spin to choose a value, to collapse from superposition into a definite state. The mathematics that describes this superposition involves those spinors we talked about, 2-component complex numbers that encode all possible spin states. We can write any spin state as a combination of spin up and spin down along some chosen axis, with complex numbers telling us the quantum amplitudes for each possibility. These aren't probabilities, they're something more subtle, probability amplitudes, which can be positive or negative, real or imaginary. Only when we square their magnitudes do we get actual probabilities for measurement outcomes. This is where the 720-degree rotation mystery becomes most vivid. When you rotate a spinor by 360 degrees, all the probability amplitudes pick up a minus sign. If the state was 0.6x spin up plus 0.x spin down before the rotation, it becomes just a 6x spin up 0.8x spin down after. The relative proportions haven't changed, and if you calculate the probabilities by squaring the magnitudes, you get the same values. In that sense, the physical state seems unchanged, but the minus sign is real and has observable consequences in interference experiments. To see why this minus sign matters, imagine splitting a beam of electrons into 2 paths, rotating one path by 360 degrees, and then recombining them. Where the 2 beams meet, their spinor wave functions interfere. Without the rotation, they might interfere constructively, reinforcing each other. But the 360-degree rotation introduces a minus sign in one beam, turning constructive interference into destructive interference. The electrons avoid regions where they would have accumulated without the rotation and accumulate where they would have cancelled. The entire pattern shifts, providing direct evidence of the minus sign. This has actually been observed in beautiful experiments with neutrons, which are also spin 1-2 particles. Using magnetic fields to rotate the neutron spins and crystal interferometers to split and recombine neutron beams, physicists have directly verified that a 360-degree rotation introduces a minus sign, while a 720-degree rotation returns the state to its original form. It's not just theoretical, it's experimentally confirmed reality. The belt trick or plate trick I mentioned earlier gives us a mechanical analogy for this behaviour. Take a book and attach ribbons from it to the walls around you. Rotate the book 360 degrees and the ribbons become twisted. But, and this is the surprising part, if you rotate the book another 360 degrees in the same direction, you can untwist all the ribbons without any further rotation. The book needs 2 complete turns to return both itself and its connections to the surrounding space to their original configuration. Mathematicians call this property of needing 2 rotations to return to the start double connectivity. Our ordinary 3D rotation space, SO3, is doubly connected, meaning there are 2 fundamentally different ways to go from any orientation to any other orientation, differing by a 360-degree rotation. SU2, the space where spinors live, unwraps this double connectivity. In SU2, these 2 paths become distinct, and spinners can tell the difference between them. This mathematical structure has profound physical consequences. It's the reason electrons are fermions, particles that obey the Pauli exclusion principle. The connection between the 720-degree rotation property and the exclusion principle isn't coincidental. It's mandated by the spin statistics theorem, one of the most important results in quantum field theory. This theorem proves that particles needing 2 rotations to return to their original state, half-integer spin particles, must be fermions, while particles needing only 1 rotation, integer spin particles, must be bosons. The difference between fermions and bosons shapes the entire structure of our universe. Fermions, like electrons, protons, and neutrons, can't occupy the same quantum state. This exclusion leads to the shell structure of atoms, the periodic table of elements, the stability of matter. Bosons, like photons and helium-4 atoms, can all pile into the same quantum state, leading to phenomena like laser light and Bose-Einstein condensation. All of this emerges from the geometry of rotations in quantum mechanics, from whether a particle sees the full SU2 structure or only its SO3 shadow. Let's think more carefully about what happens during these rotations. When we rotate an electron's spin state, we're not physically grabbing the electron and turning it. Remember, it's not actually spinning in space. Instead, we're changing our reference frame, or equivalently, applying a magnetic field that causes the spin to precess. The rotation happens in the abstract space of quantum states, in the 2-dimensional complex vector space where spinors live. In this space, rotations are implemented by 2 Caylus-2 complex matrices, the fundamental representation of SU2. These matrices act on the 2-component spinors, mixing the spin-up and spin-down components in precisely determined ways. A rotation by angle θ around the z-axis multiplies spin-up by E-Yask if2 and spin-down by E-Bun if2. Notice the factor of 1,2 in the exponent. This is why a 360-degree rotation, θ 2p, gives a minus sign, E-Gen IP, 1, while a 720-degree rotation, θ 4p, gives back the original state, E-Gen 2p, 1. This factor of 1,2 appears everywhere in the physics of spin 1,2 particles. The electron has spin angular momentum (2), half of the fundamental quantum unit. When measuring spin along any axis, we get +2, half-integer multiples of. In magnetic fields, the energy splitting is proportional to 1,2. It's as if spin 1,2 particles live at half the pace of the classical world, needing twice as much rotation to complete their cycles. But why should nature include such particles? Why not just have integer spin particles that behave more classically? The answer seems to be that half-integer spin is essential for the structure of matter. Without fermions, without the exclusion principle, atoms would collapse, chemistry wouldn't exist, and the universe would be a very different place. The universe needs both types of particles, fermions to build structure and bosons to mediate forces and carry energy. The interplay between fermions and bosons creates the rich tapestry of physics we observe. Electrons, fermions, bound in atoms can emit and absorb photons, bosons, leading to atomic spectra. Quarks, fermions, bind together via gluons, bosons, to form protons and neutrons. The W and Z bosons mediate the weak nuclear force between fermions, enabling nuclear decay and the nuclear fusion that powers stars. Every interaction in particle physics involves this dance between fermions and bosons, between particles that exclude each other and particles that can congregate. In condensed matter physics, the collective behavior of many spins leads to remarkable phenomena. In ferromagnets, electron spins align parallel, creating macroscopic magnetism. In antiferromagnets, neighbouring spins align antiparallel, cancelling each other's magnetic moments but creating a different kind of order. In frustrated magnetic systems, geometric constraints prevent all spin interactions from being satisfied simultaneously, leading to exotic states like spin liquids and spin ice. One of the most fascinating applications of spin physics is in the field of spintronics, electronics based on spin rather than charge. In ordinary electronics, we control the flow of electric charge to process and store information. In spintronics, we manipulate the spin of electrons. Giant magnetoresistance, which reads data from hard drives, depends on how electron scattering changes depending on the relative alignment of spins in magnetic layers. Spin transfer torque can flip magnetic domains using spin-polarized currents, potentially leading to new types of computer memory. Even more exotic is the field of topological spintronics, where the geometric properties of spin textures in materials lead to protected electronic states. Skyrmions, whirlpool-like spin configurations, can exist in certain magnetic materials and might be used for ultra-dense data storage. The quantum spin Hall effect creates edge states where electrons with opposite spins travel in opposite directions, protected from scattering by topological constraints. As we contemplate these applications from the practical to the exotic, we see how the abstract mathematics of SU2 and spinors translates into real phenomena, real technologies, real possibilities for the future. The same 720-degree rotation property that seems like an abstract mathematical curiosity underlies the stability of matter, the functioning of MRI machines, the storage of data on hard drives, and potentially revolutionary new technologies we're just beginning to imagine. But let's return to the conceptual heart of our mystery. We've been talking about rotations, but what exactly is rotating when we rotate a spin? Since the electron isn't physically spinning, what does it mean to rotate its spin state? The answer is subtle and profound. We're rotating the spin state in an abstract space of possibilities, changing how it's oriented relative to our measurement apparatus, changing what outcomes we'd get if we measured along different axes. Think of it this way. The spin state encodes the probability amplitudes for getting up or down along every possible measurement axis. When we rotate the spin state, we're reshuffling these probability amplitudes in a very specific way, one that preserves the total probability, which must always equal 1, and maintains the proper relationships between measurements along different axes. Thus, rotation isn't happening in physical space, but in the space of quantum possibilities. This abstract nature of spin rotations connects to a deeper principle in quantum mechanics, the principle of gauge invariance. The overall phase of a quantum state, whether we write it as p's or efficiency key, doesn't affect any measurable quantities. Probabilities depend on Riost, which is the same regardless of the phase. This gauge freedom is related to the conservation of electric charge and more generally to the fundamental forces of nature. For spinors, the gauge structure is richer because of the SU2 symmetry, local SU2 gauge invariance, the requirement that physics shouldn't change if we perform different SU2 rotations at different points in space leads directly to the theory of the weak nuclear force. The W and Z bosons that mediate weak interactions are the gauge bosons of SU2 symmetry. In this sense, the strange rotation properties of spin are intimately connected to one of the 4 fundamental forces of nature. This connection between abstract symmetries and physical forces is one of the most beautiful discoveries in 20th century physics. It tells us that the forces of nature aren't arbitrary additions to the particle content of the universe, but necessary consequences of gauge symmetries. Electromagnetism emerges from U1 gauge symmetry, the weak force from SU2, the strong force from SU3. These gauge theories all follow the pattern first established in our understanding of spin and rotations. As we near the end of this contemplation of spinors and their twice around the circle mystery, it's worth reflecting on how far we've travelled from our starting point. We began with the simple observation that electrons behave as if they're spinning, even though they're not. We've journeyed through experimental evidence, abstract mathematics, and physical applications, seeing how this seemingly simple property connects to the deepest structures of physics. The 720-degree rotation property of spin-1,2 particles is no longer just a mathematical curiosity, but a fundamental feature of our universe, one that shapes the structure of matter, enables the technologies we depend on, and hints at even deeper symmetries underlying the laws of nature. It's a perfect example of how the universe consistently surprises us, how it operates according to principles more subtle and beautiful than our everyday experience would suggest. And perhaps there's a lesson here about the nature of understanding itself. We can never visualize spin in the classical sense, never picture it as a little ball rotating. But through patient observation, careful mathematics, and creative analogies, we can develop a different kind of understanding, one that embraces the mystery rather than trying to eliminate it, one that finds beauty in abstraction, one that accepts that the universe is under no obligation to conform to our evolved intuitions. As you lie there in the darkness, perhaps you can feel a shift in your relationship with the mysterious. The fact that every electron in your body, every proton and neutron in every atom, carries this strange spin that isn't spinning. It's no longer a problem to be solved, but a feature to be appreciated. The universe has hidden depths, secret structures, and mathematical beauty that we're only beginning to uncover. And spin, with its requirement for 2 full rotations to return home, is our gentle introduction to these quantum mysteries. Let's drift now into the quiet laboratories where spin reveals itself in ever more subtle ways, where patient scientists coax nature into showing us new facets of this quantum jewel. We've seen the dramatic splitting of atomic beams, the precise resonances of spinning particles in magnetic fields, but there are so many more ways that spin whispers its secrets to those who know how to listen. Each experiment is like a gentle conversation with the universe, a careful question posed in the language of magnetic fields and radio waves, answered in the soft clicks of detectors and the delicate traces on oscilloscope screens. Consider electron spin resonance again, but now let's feel our way more deeply into what's actually happening. Picture a single electron, trapped perhaps in a crystal defect or at the heart of the organic molecule. Around it, a strong magnetic field creates a preferred direction in space, like a cosmic compass needle pointing north. The electron's spin can align with this field, spin up lower energy, or against it, spin down higher energy. The energy difference is tiny, corresponding to microwaves rather than visible light, but it's absolutely precise, determined by fundamental constants of nature. Now we bathe this electron in microwaves, electromagnetic waves oscillating billions of times per second. Most frequencies pass by without effect, like radio stations you're not tuned to. But at exactly the right frequency, when the microwave photon energy exactly matches the gap between spin up and spin down, something magical happens. The electron absorbs the photon and flips its spin. It's a quantum transition, instantaneous and complete. Not a gradual turning, but a sudden jump from one state to another. What makes ESR so powerful is that the exact resonance frequency depends on the electron's environment. Nearby atoms, chemical bonds, other electrons, all create small magnetic fields that add to or subtract from the external field, shifting the resonance frequency slightly. These shifts are like fingerprints, unique signatures that tell us about the electron surroundings. A free radical in a damaged protein has a different ESR signature than one in healthy tissue. An electron in a semiconductor quantum dot resonates differently than one in a carbon nanotube. Each environment leaves its mark on the spin dynamics. In the 1960s, scientists discovered they could do even more sophisticated things with spin, resonance. Instead of just flipping spins, they could create coherent superpositions, states where the spin is literally pointing up and down simultaneously. By applying carefully timed pulses of microwaves, they could rotate spins by any angle, not just flip them 180 degrees. A 90-degree pulse creates an equal superposition of up and down. The spin isn't confused or uncertain, it's in a definite quantum state that happens to be a superposition. These coherent spin states can be manipulated with exquisite precision. Pulse sequences with names like Hahn echo, CPMG, and COSY can refocus spin evolution, reverse the effects of environmental noise, or correlate spins in different parts of a molecule. It's like choreographing a ballet where the dancers are individual atomic spins, and the music is carefully orchestrated magnetic field pulses. Every step is precisely timed, every movement calculated to produce the desired final configuration. This level of control has made nuclear magnetic resonance, NMR, one of the most powerful tools in chemistry and biochemistry. While ESR works with electron spins, NMR typically uses nuclear spins, particularly the spin 1 to surf nuclei of hydrogen atoms. The principles are the same: spins in magnetic fields, resonance at specific frequencies, environmental shifts that provide information. But because nuclear spins are much weaker magnets than electron spins, NMR requires stronger magnetic fields and works at radio frequencies rather than microwaves. The medical application of NMR, magnetic resonance imaging or MRI, is perhaps the most visible triumph of spin physics. When you lie in an MRI scanner, you're surrounded by a magnetic field tens of thousands of times stronger than Earth's. This field aligns a tiny fraction of the hydrogen nuclei in your body's water molecules, creating a faint but detectable nuclear magnetization. Radio frequency pulses flip these spins, and as they relax back to equilibrium, they emit radio waves that carry information about their environment. Different tissues have different relaxation times, how quickly the spins return to equilibrium after being disturbed. Fat relaxes differently than muscle, tumours differently than healthy tissue, flowing blood differently than stationary tissue. By measuring these relaxation times with various pulse sequences, MRI can create detailed three-dimensional images of soft tissue with extraordinary contrast and resolution. Every image is essentially a map of nuclear spin dynamics in your body. But MRI is just the beginning. Functional MRI, fMRI, can detect the changes in blood oxygenation that accompany neural activity, allowing us to watch the brain think in real time. Diffusion MRI can track the movement of water molecules, revealing the white matter highways that connect different brain regions. Magnetic resonance spectroscopy can identify and quantify specific molecules, turning the scanner into a non-invasive chemistry lab that can detect metabolic changes associated with disease. The development of these techniques required not just understanding spin, but learning to manipulate it with incredible sophistication. Modern MRI pulse sequences involve hundreds of precisely timed radio frequency pulses and magnetic field gradient switches, all calculated to extract specific information from the nuclear spins. It's a testament to how far we've come from Stern and Gerlach's simple, beam-splitting experiment to these complex symphonies of spin manipulation. Moving from medical applications to materials science, spin continues to surprise us with new phenomena. In the 1980s, scientists discovered giant magnetoresistance, GMR, in thin films of alternating magnetic and non-magnetic layers. When the magnetic layers have parallel magnetization, electrons can pass through easily. When they're anti-parallel, electrons with different spins scatter differently, dramatically increasing the electrical resistance. This spin-dependent scattering can change the resistance by factors of 10 or more, hence giant magnetoresistance. GMR revolutionized computer hard drives, allowing much denser data storage. The read head in a modern hard drive is essentially a GMR sensor that detects the magnetic fields from tiny magnetic domains on the spinning disk. Each domain represents a bit of information, its magnetization direction encoding a 0 or 1. As the domains got smaller to increase storage density, the magnetic fields got weaker, but GMR sensors became sensitive enough to detect them. The multi-terabyte hard drives we take for granted today wouldn't be possible without our understanding of how electron spins interact with magnetic materials. The discovery of GMR opened up the entire field of spintronics, electronics based on spin rather than just charge. In conventional electronics, we control the flow of electric charge to process information. In spintronics, we also control the spin of the electrons. This adds a new degree of freedom, a new way to encode and process information. Spin-polarized currents, where most electrons have their spins aligned, can be generated and detected. Spin currents, where up spins flow one way and down spins flow the other with no net charge current, are possible. These exotic currents open up new possibilities for low-power electronics and quantum computing. One of the most promising spintronic devices is the Spin Transfer Torque Magnetic Random Access Memory, STT-MRAM. In these devices, a spin-polarized current can flip the magnetization of a small magnetic element, writing information. The magnetization state can be read using magnetoresistance effects. Unlike conventional RAM, STT-MRAM is non-volatile. It retains information without power. It's also faster and more durable than flash memory. Commercial STT-MRAM products are already available, with densities and speeds improving rapidly. Even more exotic spintronic phenomena are being discovered in new materials. Topological insulators have insulating interiors, but conducting surfaces where electron spins are locked perpendicular to their momentum. This spin momentum locking is protected by topology, the mathematical structure of the electronic states, making it robust against disorder and impurities. Electrons on these surfaces can carry spin information without dissipation, potentially enabling ultra-low-power spintronic devices. In magnetic skyrmions, spins arrange themselves in nanoscale whirlpool patterns that are topologically protected from decay. These skyrmions can be moved with electric currents much smaller than those needed to move magnetic domain walls, making them promising for ultra-dense low-power data storage. Researchers have demonstrated skyrmion creation, manipulation, and detection, bringing skyrmion-based devices closer to reality. The quantum nature of spin becomes even more apparent in experiments with individual spins. Using techniques like scanning tunneling microscopy with spin-polarized tips, scientists can now image and manipulate individual atomic spins on surfaces. They can arrange atoms to create artificial spin structures, design magnets with properties not found in nature. They can watch individual spins flip, measure their coherence times, even perform quantum operations on them. In quantum dots, tiny islands of semiconductor that trap individual electrons, researchers have achieved remarkable control over individual electron spins. They can initialize spins in specific states, rotate them with microwave or optical pulses, and read them out with high fidelity. 2-qubit gates, where the state of one spin controls operations on another, have been demonstrated. These quantum dot spins are leading candidates for qubits in future quantum computers. The coherence time of these spins, how long they maintain quantum superposition before environmental noise destroys it, has improved dramatically. In isotopically purified silicon-28, which has no nuclear spins to create magnetic noise, electron spins can maintain coherence for seconds. Nuclear spins in silicon can maintain coherence for minutes or even hours. These long coherence times make spin-based quantum computing increasingly practical. Nitrogen vacancy, NV, centers in diamond are another remarkable spin system. These are defects where a nitrogen atom replaces a carbon and an adjacent carbon is missing, creating a trapped electron spin. What makes NV centers special is that their spin states can be initialized and read out optically, with laser light, even at room temperature. They're like atomic-scale lighthouses whose color depends on their spin state. NV centers are being used as quantum sensors of unprecedented sensitivity. A single NV center can detect the magnetic field from a single nuclear spin nanometers away. Arrays of NV centers can image magnetic fields with nanoscale resolution, revealing the structure of magnetic materials, the currents in biological neurons, even the magnetic signatures of individual molecules. It's like having an MRI scanner that works at the scale of atoms rather than millimeters. The strange quantum properties of spin become even more pronounced in experiments with entangled spins. When two spins are entangled, measuring one instantly affects the other, no matter how far apart they are. This spooky action at a distance, as Einstein called it, has been verified in countless experiments. Entangled electron spins have been created and maintained in quantum dots separated by micrometers. Entangled photon spins have been distributed over hundreds of kilometers through optical fibers and even from satellites to ground stations. These entangled spin states are the resource that powers quantum information processing. Quantum teleportation, where the state of one spin is transferred to another distant spin using entanglement, has been demonstrated. Quantum key distribution, using the spin states of photons to create provably secure encryption keys, is already commercially available. Quantum computers based on spin qubits are being developed by major technology companies and startups alike. But perhaps the most profound spin experiments are those that probe the foundations of quantum mechanics itself. Tests of Bell inequalities using entangled spins have definitively ruled out local hidden variable theories. The universe really is non-local at the quantum level. Experiments on geometric phases, where spins acquire phase shifts from cyclic evolution even without dynamics, reveal the deep geometric structure of quantum mechanics. Studies of spin decoherence illuminate how quantum systems become classical through interaction with their environment. In ultra-cold atom experiments, researchers can create artificial magnetic fields for neutral atoms by rotating them or using carefully arranged laser fields. These synthetic magnetic fields affect the atom's spins, just like real magnetic fields, but with unprecedented control. Researchers can dial up exotic spin-orbit couplings, create artificial dimensions, even simulate the physics of electrons in solids using atoms that are 1 billion times larger and 1 trillion times slower. These ultra-cold atom systems allow us to explore spin physics in regimes impossible to reach with electrons. Spain-Bose-Einstein condensates, where billions of atoms share the same spin state, exhibit phenomena like spin domains, spin waves, and topological defects. Degenerate Fermi gases with controllable spin interactions can simulate high-temperature superconductors, quantum magnets, and other strongly correlated materials that are too complex to understand theoretically or simulate on classical computers. The universality of spin, the fact that it appears in so many different contexts with the same mathematical structure, continues to amaze physicists. Whether we're looking at electrons in atoms, quarks in protons, atoms in optical, lattices, or even collective excitations in solids, we find the same SU2 symmetry, the same commutation relations, the same peculiar requirement for 720-degree rotations. It's as if spin is one of the universe's favourite motifs, a pattern it uses again and again at different scales and in different contexts. As we contemplate this vast experimental landscape, from medical scanners to quantum computers, from hard drives to ultra-cold atoms, we see how the abstract mathematics of spin transforms into concrete technology and deep understanding. Every experiment confirms the quantum mechanical description of spin while revealing new phenomena, new applications, new questions. The dialogue between theory and experiment continues, each informing and inspiring the other. The precision of these experiments is breathtaking. Magnetic moments are measured to parts per trillion. Coherence times are extended from microseconds to hours. Individual spins are controlled with errors below 1 part in 10,000. This isn't just technological achievement, it's a testament to how well we understand spin, how accurately quantum mechanics describes this fundamental property of matter. And yet, for all our understanding and control, spin retains its essential mystery. We can predict its behavior with extraordinary precision, manipulate it with remarkable sophistication, build technologies that depend on it, but we still can't visualize it, still can't reduce it to classical concepts. It remains genuinely quantum mechanical, a bridge between our everyday world and the strange realm of quantum physics. Now we step back from the technical details, the experiments and applications, to contemplate something perhaps even more mysterious. What does it mean that we, conscious beings made of spinning particles, can contemplate spin itself? Here in the quiet darkness, as your breath slowly deepens and your thoughts begin to soften around the edges, we can explore the philosophical implications of spin, the strange loop of matter understanding itself, of quantum systems studying quantum mechanics. Your brain, that 3 pounds of warm, wet matter resting on your pillow, contains roughly 10^27 electrons, each carrying its quantum spin through the night. These electrons flow through neurons, creating the electrical currents that somehow, and nobody really knows how, give rise to thoughts, feelings, consciousness itself. The spin states of these electrons affect chemical reactions, influence molecular binding, perhaps even play a role in the still mysterious process by which electrochemical activity becomes subjective experience. There's something profound about the fact that assemblies of particles obeying quantum mechanical rules have developed the ability to discover those very rules. The universe has evolved structures complex enough to study their own foundations. Through us, the cosmos develops self-awareness, uses mathematics to describe itself, performs, experiments to test its own nature. We are the universe's way of understanding spin, among other things. But this understanding comes with a peculiar limitation. Our brains evolved to navigate the macroscopic world, to track moving objects, recognize patterns, avoid predators, find food and mates. Nothing in our evolutionary history prepared us to intuit quantum mechanics. We have no mental machinery for directly perceiving superposition, no cognitive modules for visualizing spinors, no intuitive grasp of 720-degree rotations returning to the start. Our minds are classical computers trying to understand quantum phenomena, and yet, through the extraordinary power of mathematical reasoning and experimental investigation, we've transcended these limitations. We can't visualize an electron spin, but we can describe it mathematically with perfect precision. We can't intuit quantum superposition, but we can measure it, manipulate it, use it. The mathematics becomes a kind of prosthetic imagination, allowing us to reach beyond what our evolved brains can directly grasp. This raises deep questions about the nature of understanding itself. Do we really understand spin if we can't visualize it? Is mathematical description enough? Or is there something crucial missing when we can't form mental pictures? Different physicists have different philosophical positions on this. Some say the mathematics is the complete understanding. If you can calculate correctly, you understand fully. Others feel that without intuitive grasp, our understanding remains somehow incomplete. Perhaps the issue isn't that our understanding is incomplete, but that we're using too narrow a definition of understanding. Maybe understanding doesn't require visualization. After all, we say we understand love, justice, beauty, consciousness, none of which can be adequately visualized or reduced to simple pictures. Understanding might be more about grasping relationships, patterns and structures than about forming mental images. The way spin challenges our classical intuitions might actually be valuable, forcing us to expand our concepts of knowledge and understanding. It's humbling to realize that reality operates according to principles we can't directly perceive, that our everyday experience is a limited window onto a far stranger universe. This humility is perhaps the beginning of wisdom, recognizing that the universe is under no obligation to conform to our expectations or limitations. Consider how the discovery of spin changed our view of matter itself. Before quantum mechanics, particles were thought of as tiny balls with properties like mass and charge attached to them. Spin revealed that particles have internal degrees of freedom that don't correspond to anything in classical physics. This led to a fundamental reconceptualization. Particles aren't objects with properties, but rather excitations in quantum fields, and their properties are really just labels for how these excitations transform under various symmetries. This shift from particles as things to particles as excitations is profound. It suggests that the fundamental level of reality isn't made of stuff, but of patterns, relationships, mathematical structures. Spin isn't something an electron has. In a sense, spin is part of what an electron is. The electron is a particular kind of excitation in the electron field, one that transforms as a spin 1-2 representation of the Lorentz group. The mathematics isn't describing the particle. The mathematics is the particle. This mathematical nature of reality connects to ancient philosophical questions. Is mathematics discovered or invented? Do mathematical structures exist independently of human minds? If particles are mathematical structures, does this mean the physical world is ultimately mathematical? These questions have no easy answers, but spin provides a concrete example of how deeply mathematics is woven into the fabric of reality. The fact that we can ask these questions at all is remarkable. Here we are, patterns of matter and energy that have become complex enough to recognize patterns, to use language, to create mathematics, to wonder about our own nature. Every atom in your body except hydrogen was forged in the nuclear furnaces of stars, the calcium in your bones, the iron in your blood, the carbon in your DNA. All were created in stellar cores and scattered through space in supernova explosions. You are literally made of stardust, and that stardust has arranged itself into a pattern that can contemplate its own origins. And throughout this cosmic journey, from the Big Bang to stars to planets to life to consciousness, spin has been there. The protons and neutrons that formed in the first seconds after the Big Bang had spin. The nuclear reactions in stars depend on spin. The chemistry that led to life involves spin. The thoughts you're thinking right now involve electrons with spin. It's a thread running through the entire history of the universe, a quantum property that has been essential at every stage. The stability of matter itself depends on spin through the Pauli exclusion principle. Without it, electrons would all collapse into the lowest energy orbital, atoms would be impossibly small and dense, chemistry as we know it couldn't exist. The fact that you exist as a stable arrangement of atoms, that your body maintains its structure from moment to moment, is a direct consequence of electron spin and the exclusion principle. In a very real sense, spin is part of what makes you possible, but spin's role in biology might go even deeper. Some researchers have proposed that quantum coherence, including spin coherence, might play a role in biological processes. Photosynthesis appears to involve quantum coherent energy transfer. Some birds seem to navigate using quantum entanglement in certain proteins that can sense magnetic fields. The exact mechanisms are still being worked out, but it's increasingly clear that life doesn't always decohere quantum effects. Sometimes it exploits them. There's even speculation that consciousness itself might involve quantum processes, perhaps including spin. The idea is controversial and unproven, but it's intriguing to consider that the same quantum properties that make matter stable might also be involved in making matter aware. Could the mysterious, hard problem of consciousness, how subjective experience arises from objective processes, be related to the quantum mechanical nature of matter? We don't know, but spin would almost certainly be involved if quantum mechanics plays a role in consciousness. Whether or not consciousness is quantum mechanical, there's no doubt that our ability to think about spin, to discover it, understand it, and use it represents something extraordinary in the history of the universe. Through us, the universe has developed the capacity for self-reflection, for mathematical reasoning, for experimental investigation. We are the cosmos looking at itself in the mirror, using tools like particle accelerators and MRI scanners to examine its own structure. This capacity for self-examination extends beyond physics to encompass all of human knowledge and culture. Art, literature, music, philosophy all represent different ways the universe explores itself through us. But physics, and particularly quantum mechanics, represents perhaps the deepest probe into the nature of reality, and spin, with its irreducibly quantum nature, takes us to the heart of this investigation. The discovery and understanding of spin required not just individual brilliance, but collective effort over generations. From Stern and Gerlach's first experiments to today's quantum computers, thousands of scientists have contributed, each built on the work of others, sharing knowledge through papers and conferences, teaching students who would make the next discoveries. Science is a collective enterprise, a communal attempt to understand reality. In studying spin, humanity acts as a single distributed cognitive system, pooling our intellectual resources to grasp something no individual could fully comprehend alone. This collective nature of scientific understanding raises interesting questions about knowledge. Who understands spin? Individual physicists, the physics community, humanity as a whole? The knowledge is distributed across many minds, recorded in textbooks and papers, embedded in technologies. No single person holds all of it. In a sense, it's humanity's collective consciousness that understands spin, not any individual human. And this understanding continues to evolve. Each new experiment reveals new facets of spin. Each theoretical advance provides new perspectives. Our understanding today is far deeper than in Pauli's time, and future generations will likely understand aspects we can't yet imagine. Knowledge of spin, like all scientific knowledge, is provisional, always subject to refinement and extension. We're not discovering eternal truth so much as developing increasingly accurate and useful models. But even our current, incomplete understanding of spin has given us remarkable power. We can manipulate individual spins, create entangled states, build devices that exploit quantum coherence. This technological mastery might seem to suggest we've conquered the quantum realm, bent it to our will. But perhaps it's more accurate to say we've learned to work with quantum mechanics, to respect its rules and exploit its possibilities. We haven't conquered spin, we've become partners with it. This partnership between human consciousness and quantum mechanics extends beyond technology to shape our worldview. The discovery that reality is fundamentally probabilistic, that properties don't have definite values until measured, that entanglement allows instant correlations across space. These insights have philosophical implications that we're still working through. Spin, as one of the simplest quantum systems, has been central to developing and testing these ideas. the cultural impact of quantum mechanics, including spin, extends beyond physics and philosophy. Quantum concepts have influenced art, literature, and popular culture, even if not always accurately. The idea that reality is fundamentally uncertain, that observation affects what's observed, that particles can be in multiple states simultaneously. These ideas have resonated far beyond physics, becoming metaphors for everything from human relationships to business strategies. Of course, most popular uses of quantum concepts are metaphorical rather than literal. But even as metaphors, they reflect how quantum mechanics has changed our cultural understanding of reality. We now live in a world where it's common knowledge that matter is mostly empty space, that particles can be in two places at once, that the universe is fundamentally probabilistic. Spin, with its rotation that isn't rotation, contributes to this sense that reality is far stranger than everyday experience suggests. As you lie there contemplating these ideas, perhaps you can feel your own strange position in the universe. You're made of quantum particles, including countless electrons with spin. Your thoughts emerge from quantum processes in your brain. You're contemplating spin using a mind made of spinning particles. It's a beautiful circularity, a strange loop of matter contemplating itself. And in this contemplation, perhaps we find meaning. Not meaning imposed from outside, but meaning that emerges from the universe's own structure. The fact that matter can organize itself into patterns complex enough to understand their own quantum nature, isn't that a kind of cosmic significance? Through us, the universe achieves self-awareness, creates beauty, experiences wonder. Spin is part of the story of how dead matter becomes living, thinking, questioning beings. This doesn't answer all our existential questions, but it does suggest that we're not separate from the universe but expressions of it. The same physical laws that govern spin govern our neurons. The same quantum mechanics that describes electron states describes the molecules of life. We're not outsiders studying an alien universe, we're the universe studying itself. And in that self-study, meaning emerges, not as something external to physics, but as something that arises from it. Now, as the night deepens around you and your breathing becomes even slower, even more peaceful, let's gently revisit everything we've discovered about spin, allowing it all to settle into your mind like sediment, drifting to the bottom of a still pond. There's no need to grasp tightly to any particular concept or struggle to remember every detail. Instead, let the ideas wash over you. Let the mystery of spin become a comfortable companion in these quiet hours. We began our journey with a simple observation that became a profound puzzle. Electrons behave as if they're spinning, carrying angular momentum, creating magnetic fields, yet they cannot actually be rotating in any classical sense. If they were tiny spinning spheres, their surfaces would need to exceed the speed of light. They would radiate away their energy. They would violate the fundamental laws of physics that govern our universe. And so we were forced to accept something far stranger, that spin is an intrinsic property, a kind of angular momentum that exists without angular motion. Think about that for a moment, but gently, without strain. Angular momentum without angular motion. It's like having the essence of rotation without the actual rotating, like capturing the abstract idea of spinning and building it directly into the fabric of particles. The universe has taken a concept we thought we understood. Things that spin have angular momentum, and shown us that the connection can run the other way. Particles can have angular momentum as a fundamental property, and this makes them behave as if they were spinning, even though they're not. The Stern-Gerlach experiment showed us that this spin is quantized in a particularly striking way. When we measure spin along any direction, we get only two possible answers, up or down along that axis, plus 2 or quertus, nothing in between. The universe insists on this discreteness, this digital rather than analog nature of spin measurement. It's not that our instruments aren't precise enough to measure intermediate values, it's that intermediate values don't exist. The quantum world is discrete in ways our classical intuitions don't prepare us for. And then, there's the way spin measurements along different axes interfere with each other. Measure spin along the vertical axis, and you know it precisely. But this measurement destroys any knowledge of the spin along horizontal axes. Measure horizontally, and you lose the vertical information. It's not clumsiness or instrumental limitation, it's a fundamental feature of quantum mechanics, encoded in the non-commuting algebra of spin operators. The universe has an irreducible uncertainty built into its structure, a fuzziness that no amount of careful measurement can eliminate. We discovered that spin lives in an abstract mathematical space described by the group SU2, where rotations have a peculiar property. You need to rotate 720 degrees, not just 360, to truly return to your starting point. After one complete rotation, a spin 1-2 particle's quantum state has picked up a minus sign. Only after a second complete rotation does it return to its original state. This isn't just mathematical abstraction, it has real, measurable consequences in interference experiments. The universe really does have this hidden doubling in its rotational structure. This strange rotation property is intimately connected to the division of particles into fermions and bosons. Fermions, with their half-integer spins, obey the Pauli exclusion principle. No two can occupy the same quantum state. This exclusion is what gives atoms their structure, makes chemistry possible, prevents matter from collapsing. Bosons with integer spins can all pile into the same state, making possible phenomena like laser light and Bose-Einstein condensation. The entire structure of matter and forces emerges from this distinction rooted in spin. We've seen how spin appears everywhere in physics, from the smallest to the largest scales. In atomic physics, spin-orbit coupling creates the fine structure in spectral lines. In nuclear physics, the spins of protons and neutrons determine nuclear properties. In particle physics, spin is one of the fundamental labels that characterize elementary particles. In condensed matter physics, collective spin behavior creates magnetism, superconductivity, and exotic quantum phases. In cosmology, the spin statistics of particles in the early universe affected the formation of elements and structures. The technological applications of spin surround us, even if we rarely think about them. Every time you have an MRI scan, nuclear spins in your body are being manipulated and measured. Every time you save a file on a hard drive, electron spins are encoding your data. Every time you use a computer, transistors that depend on quantum mechanics, including spin, are processing information. The abstract mathematics of spin has become concrete technology that shapes our daily lives. But perhaps most remarkably, we've seen how spin connects to the deepest questions in physics. The relationship between spin and statistics emerges from the structure of relativistic quantum field theory. The gauge theories that describe fundamental forces have their roots in the same mathematical structures that describe spin. The ongoing quest to understand quantum gravity, to unify quantum mechanics with general relativity, must grapple with spin. Every attempt to understand reality at its most fundamental level encounters spin as an essential feature, and through it all runs this thread of mystery, this irreducible quantum strangeness that we can describe mathematically but can't visualize classically. We cannot picture an electron spin because there's nothing to picture in the classical sense. It's not a failure of imagination but a recognition that reality operates according to principles beyond our evolved intuitions. The universe is quantum mechanical at its base, and spin is perhaps the clearest window into this quantum nature. As these ideas settle into your mind, notice how your relationship with mystery might be shifting. We often think of mysteries as problems to be solved, puzzles to be figured out, unknown to be made known. But spin teaches us that some mysteries are features, not bugs. The universe's quantum nature isn't a veil obscuring classical reality. It is reality. The mystery isn't something to be eliminated, but something to be appreciated, explored, lived with. This comfort with mystery, this ability to work with concepts we can't visualize, represents a kind of intellectual maturity. Children need concrete pictures, tangible examples. But as our understanding deepens, we learn to work with abstraction, to let mathematics guide us where intuition fails. The history of physics is partly a history of letting go of the need for mechanical models, of accepting that reality might be more mathematical than mechanical. And yet, we haven't given up on understanding. We've just expanded what understanding means. We understand spin through its mathematics, its experimental signatures, its technological applications, its connections to other physics concepts. We understand it through analogies and metaphors, even if they're imperfect. We understand it through the patterns it creates, the problems it solves, the questions it raises. This is a richer, more multifaceted understanding than any simple mechanical picture could provide. Let your mind drift now through the landscape of spin we've explored. Picture, if you can, not the spinning itself, but the effects. atomic beams splitting in two, nuclear spins flipping in MRI scanners, electron spins aligning in magnets, quantum computers manipulating individual spins. See the mathematical symbols encoding spin states, the experimental apparatus measuring spin components, the theoretical physicists working out spin's implications. All of this activity, all of this knowledge, emerging from a property that isn't quite what its name suggests. Feel how spin connects you to the cosmos. The electrons in your body, with their spin 1-2, are identical to electrons in distant galaxies. The laws governing spin in your neurons are the same laws operating in stellar cores and black hole accretion disks. When you learn about spin, you're learning about something universal, something that transcends location and time. The spin of an electron here and now follows the same rules as the spin of an electron at the universe's beginning or end. There's something deeply peaceful about these universal laws, these patterns that repeat across all of space and time. Whatever chaos and uncertainty we experience in daily life, underneath it all are these steady, reliable quantum rules. Spin will always be quantized. The exclusion principle will always hold. Angular momentum will always be conserved. These are the universe's promises to itself, the constraints it has chosen, or that chose it. As your thoughts continue to soften and slow, perhaps you can feel yourself as part of this vast pattern. You're not separate from the universe, but woven into it, made of the same quantum fields, obeying the same laws, participating in the same cosmic dance. Your consciousness, whatever its ultimate nature, emerges from the collective behavior of particles with spin. Your thoughts are patterns in the quantum substrate of reality. And in recognizing this, perhaps we find a different kind of meaning than our ancestors sought. Not meaning imposed by external purpose, but meaning that emerges from pattern and relationship, from complexity and awareness, from the universe's capacity to know itself through conscious subsystems like us. We are how the universe becomes aware of spin, among other things. We are how it discovers its own laws, appreciates its own beauty, contemplates its own mystery. This is not to make humans special in any absolute sense. Other conscious beings elsewhere in the universe, if they exist, would be equally valid expressions of cosmic self-awareness. And consciousness might not be the only way the universe achieves meaning. Perhaps there are forms of significance we can't imagine, just as we couldn't have imagined spin before discovering it. But for now, for us, consciousness studying spin represents one way the universe transcends mere existence to achieve understanding. Let these thoughts drift through your awareness without trying to hold them too tightly. Like spin itself, they might be better appreciated than grasped, better experienced than analyzed. Feel the mystery as a kind of openness, a spaciousness in your understanding that leaves room for wonder. The fact that electrons have spin 1-2, that they need 720-degree rotations to return to start, that they obey the exclusion principle. These aren't problems to solve, but features to marvel at. Notice how the technical details we discussed earlier, the mathematics of SU2, the experimental measurements of magnetic moments, the technological applications in spintronics, can now float in your awareness without demanding complete comprehension. You don't need to remember every equation or experimental setup. What matters is the overall shape of the knowledge, the recognition that spin is real, mysterious, useful, and fundamental. The details can be looked up when needed. The sense of wonder is what stays with you. As sleep approaches, perhaps you can feel a kinship with those physicists who first encountered spin. Uhlenbeck and Goudsmit proposing electron spin to explain spectral lines, not knowing they were opening a door to quantum mechanics' strangest features. Pauli working out the exclusion principle, not knowing he was explaining the stability of matter. Dirac developing the relativistic equation for electrons, predicting antimatter as a consequence of spin. Each step revealed new depths, new connections, new mysteries, and the story continues. Right now, in laboratories around the world, scientists are pushing the boundaries of spin physics. They're creating new quantum states, developing new technologies, discovering new phenomena. The spin story we've told tonight is not complete. It's still being written. Future generations will know things about spin we can't imagine, just as we know things Stern and Gerlach couldn't have dreamed of. The mystery deepens even as our knowledge expands. But for tonight, for now, it's enough to rest with what we've explored. To know that spin exists, that it's strange and beautiful, that it shapes the universe from atoms to galaxies, that it makes possible both the stability of matter and the technologies of our age. To appreciate that we, collections of particles with spin, have somehow developed the capacity to discover and contemplate spin. To feel the peaceful recursion of matter understanding itself, of the universe achieving self-awareness through structures like us. And so we come full circle, returning to our central question with deeper understanding, like coming home after a long journey and seeing familiar things with new eyes. Why is spin not really spinning, but still acts like angular momentum? The answer, we've discovered, is both simple and profound. Spin is an intrinsic quantum property that particles possess, a form of angular momentum that doesn't arise from motion through space, but from the fundamental structure of quantum mechanics itself. It behaves like angular momentum because it is angular momentum, just not the kind that comes from things actually rotating. As you lie there in the darkness, perhaps on the edge of sleep, let's contemplate this answer one more time, slowly, gently, allowing its implications to ripple through your awareness like waves on a still pond. Spin is angular momentum without angular motion. It's a property that emerges from the mathematics of quantum mechanics, from the requirement that physics be consistent under rotations, from the deep symmetries that govern our universe. It's described by the group SU2, lives in an abstract space of complex probability amplitudes, and requires 720-degree rotations for a complete turn. This isn't the answer our classical intuitions expected or wanted. We wanted to picture little spheres spinning, to have a mechanical model we could visualize and manipulate in our minds. But the universe gently, firmly, consistently told us, through experiment after experiment, reality is quantum mechanical, not classical. Particles aren't little balls with properties. They're excitations in quantum fields, and their properties are labels for how they transform under symmetries. Spin isn't something electrons do. It's part of what electrons are. All around you right now, in the atoms of your body, your blanket, the air you breathe, countless electrons carry their spin 1-2 through the night. They're not spinning in any classical sense, yet they respond to magnetic fields as if they were tiny magnets. They obey the Pauli exclusion principle, preventing atomic collapse and making chemistry possible. They participate in the quantum dances that bond atoms into molecules, molecules into materials, materials into the structured matter that makes up our world. In your brain, electrons with spin flow through neurons, their quantum properties perhaps playing subtle roles in the emergence of consciousness. We don't fully understand consciousness. It remains perhaps the deepest mystery in science. But whatever its ultimate nature, it depends on the quantum mechanics of particles with spin. Your thoughts, your awareness of these very words, emerge from patterns of activity in networks of neurons built from atoms held together by electrons, obeying the rules of quantum mechanics, including spin. Beyond your body, beyond Earth, spin continues its quiet work throughout the cosmos. In the sun's core, protons with spin 1-2 fuse together, their spins combining according to SU2 rules, releasing the energy that lights our world. In distant galaxies, electrons spiral through magnetic fields, their spins causing them to emit synchrotron radiation we can detect across billions of light years. In the cosmic microwave background, photons with spin 1 carry information about the universe's earliest moments, their polarization patterns encoding the history of cosmic inflation. Even in the vast voids between galaxies, where matter is sparse beyond imagination, spin persists. Virtual particles pop into existence and annihilate, their spins conserved in these fleeting quantum fluctuations. Neutrinos stream through empty space, their spin 1-2 unchanged by their billion-year journeys. The quantum fields that permeate all of space have spin built into their very structure, ready to manifest as particles whenever energy is available to excite them. This universality of spin, its presence at every scale and in every corner of the cosmos, tells us something profound about the nature of reality. Spin isn't an accident or a peculiarity. It's a fundamental feature of how the universe is constructed. The fact that particles have spin, that it comes in discrete units, that fermions and bosons behave differently, these aren't arbitrary rules but necessary consequences of the deep structure of quantum mechanics and relativity. The mathematical framework that describes spin, quantum field theory, is arguably humanity's greatest intellectual achievement. It combines quantum mechanics with special relativity, describes all known particles and forces except gravity, and makes predictions accurate to extraordinary precision. Every test, from the magnetic moment of the electron measured to parts per trillion, to the discovery of the Higgs boson exactly where theory predicted, confirms this framework. And spin is central to it all, determining how particles transform, how they interact, what states they can occupy. But even as we celebrate this theoretical triumph, we remain humble before the mystery. We can describe spin mathematically, predict its behavior precisely, exploit it technologically, but we can't visualize it classically. And perhaps this is as it should be. Perhaps the universe is telling us that not everything can be reduced to pictures and mechanical models. Perhaps reality is fundamentally mathematical rather than mechanical, and our mathematics has led us to truths our evolved imaginations cannot fully grasp. This limitation of visualization doesn't diminish our understanding, it enriches it. It forces us to develop new forms of intuition, mathematical rather than visual. It teaches us that understanding doesn't always mean being able to picture something. We understand love without being able to visualize it. We understand justice without having a mechanical model for it. And we understand spin through its mathematics, its experiments, its applications, even without being able to picture a particle actually spinning. As sleep draws nearer, let your mind rest with this peaceful paradox. Every electron in your body carries spin 1-2, needs 720 degrees to return to its starting state, obeys the Pauli exclusion principle, and you don't need to visualize any of this for it to be true. The universe operates according to its quantum rules whether we understand them or not, whether we're awake or asleep, whether we exist or not. There's something deeply comforting about this independence, this reliability of physical law. Right now, as your consciousness begins to fade towards sleep, the spins in your body continue their quantum existence. They don't need your attention or understanding. They simply are, following their timeless rules, participating in the vast quantum dance that underlies all of reality. Your sleeping and waking, your understanding and confusion, your very existence, all emerge from and return to this quantum substrate, where particles with spin interact according to mathematical laws we've only recently begun to decipher. Think of all the generations of humans who lived and died without knowing about spin. They were made of particles with spin. Their lives depended on spin, but they had no concept of it. And think of all the aspects of reality we don't yet understand, all the mysteries waiting to be discovered. Perhaps future generations will look back at our current understanding of spin as primitive, limited, missing crucial features we can't yet imagine. The mystery deepens even as our knowledge expands, but tonight, in this moment, you can rest in the knowledge we've gathered so far. You know that spin exists, that it's quantized, that it behaves like angular momentum without being classical rotation. You know about the Stern-Gerlach experiment, about SU2 symmetry, about the 720-degree rotation mystery. You know that spin makes matter stable through the exclusion principle, enables technologies like MRI, and connects to the deepest structures in physics. This knowledge, incomplete as it may be, is still profound, still worthy of wonder. And perhaps most wonderfully, you know that you are part of this mystery. You are not an observer standing outside the universe looking in, but a participant made of the same quantum fields, obeying the same laws, carrying the same spin. When you contemplate spin, it's the universe contemplating itself. When you wonder about quantum mechanics, it's reality wondering about its own nature. You are the cosmos awakened to self-awareness, however briefly, however incompletely. As your thoughts continue to slow and soften, drifting toward the edge of sleep, perhaps you can feel yourself settling into the vast pattern of existence. Like an electron relaxing into its ground state, finding its lowest energy configuration, you can let go of the effort to understand and simply be. The questions about spin, why it exists, why it has the properties it does, what it ultimately means, can remain open, unanswered, peaceful in their mystery. In the silence between your thoughts, in the gaps between your breaths, spin continues its eternal dance. Electrons maintain their spin 1-2, neither increasing nor decreasing, neither speeding up nor slowing down. They don't actually rotate, yet they carry angular momentum. They exist in superposition until measured, then collapse to definite states. They entangle with other particles, creating correlations that transcend space and time. All of this happens whether you're thinking about it or not, whether you understand it or not. The universe doesn't require our understanding to exist, but perhaps it achieves something special through our understanding. Through conscious beings like us, the cosmos develops the capacity for self-reflection, for appreciation of its own beauty and mystery. We are how the universe experiences wonder at its own structure. We are how it asks questions about itself, performs experiments on itself, develops theories about itself. In studying spin, we participate in the universe's self-discovery. And now, as sleep finally approaches, you can release even these thoughts. Let them drift away like clouds dissolving in a vast sky. The knowledge of spin remains, encoded in your neurons, ready to be recalled when needed. But for now, you can simply rest in the mystery, in the quiet symmetry of a universe where particles carry angular momentum without rotating, where 720-degree turns bring you home, where the mathematics of SU2 governs the behavior of every electron in existence. Somewhere in distant galaxies, stars are being born and dying, their nuclear processes governed by spin. Somewhere in laboratories, scientists are manipulating individual spins, pushing the boundaries of quantum technology. Somewhere in the quantum vacuum, virtual particles with spin are flickering into and out of existence. And here, in your body, countless particles with spin continue their patient work, maintaining the molecular structures that sustain your life, enabling the neural processes that create your consciousness, participating in the vast quantum dance that is reality itself. The universe continues its quiet work, spin included, whether we're awake or asleep. The same laws that govern the first particles after the Big Bang govern the electrons in your brain right now. The same SU2 symmetry that determines how spins combine in distant quasars determines how they combine in the molecules of your DNA. You're woven into this cosmic tapestry, inseparable from it, made of it, returning to it, and as you drift into sleep, you remain part of this quiet universe, wrapped in its laws, carried by its mysteries, gently, peacefully, into the night. The spin of every electron continues, not as classical rotation, but as something more subtle, more fundamental, a quantum property that needs no visualization, no mechanical model, only the mathematics of symmetry and the patient accumulation of experimental evidence. You can rest now, knowing that spin will continue its work while you sleep, that you'll wake to the same quantum laws, the same mysterious universe ready to be explored anew. In the darkness, in the silence, in the space between waking and sleeping, you are held by forces you cannot see, made of particles you cannot visualize, participating in processes you can describe but not picture. And perhaps this is enough to know that the mystery exists, that we're part of it, that through us it knows itself, however incompletely. The universe spins on, not really spinning but carrying angular momentum, not rotating but transforming under SU2, not mechanical but magnificently mathematical, through the night and into whatever dreams may come.